Okay, so today we're going to be talking about complicated data types, which require complicated architectures. What is an architecture? Of what? Architecture, it's of the neural network that that we have. So far we know we have simple data. So a simple data can be what's called a tabular data. What's a tabular data? Is where you have n rows, a row for each data point, and d columns, a column for each feature. So for example, you can think you have 1,000 patients, and each patient there's like the height and weight and other blood type and everything, right? And so this is the tabular data. And what is the architecture that will fit? Oh, and of course you have one label or y, right? For each, we should do n labels. So it's n labels, one for each data point. And then what is the architecture that is used for this one? For our tabular data, the architecture that we learned last week? What? An artificial neural network, which type? Regular, fully connected. That's the word I want, right? So we start with our D features and we do a fully connected network with as many hidden layers as we want and maybe some residual connections if we want them. And we end with a Y, with one outcome, remember? Do we need a picture?
Let's see a picture.
Okay. Oh. Something like this. I just wanted the one output. I like this.
So it will be binary?
Not,
You want one output for...
No, the one output can be a continuous number. It doesn't have to be binary.
No, but why do you want the output to be just the last layer to be just the output layer to be just one?
Because we have one label. Okay, so imagine here.
What do you mean by Y label? What do you mean by one label?
For every data point, we put the data point in and we get out one Y. The Y can be binary Y, 0 or 1, or it can be a continuous number, like how many more years you have left to live or whatever. But at the end, we have one Y. We could have a representation which uses a vector of Y when we have a multi-class classification. And then it's a one-hot representation of Y. We remember this, right? Excellent. So this is the simple data, and this is called a one-to-one classification problem or regression problem or whatever, modeling problem. We put in 1x into our model. The green box represents the model. We can use any model we want, right? And then we get out a y. Okay, it's one-to-one. Excellent. The first complication is when we'll have, it's a small complication, when we have two distinct but related, we'll say why but related in a second, labels per data point. So an example would be, again, going with the health data, is that for each person, we want to predict if they're, let's say, healthy or sick or have Alzheimer's or don't. That's one prediction. And how many more years left to live. Okay, so there are two labels per the participant, per person, and we want to predict both. So what's the simplest solution to do? I have a data with thousands of patients and a lot of measurements. And for each one, I have if they're sick with Alzheimer's or not, and how many more years they had until they died. And I want to predict those two outcomes for the new patient. So what's the simplest? Yeah, Reina, your thing? Yes, the simplest solution is make two neural networks, one to predict if you're sick or not, and the other one to predict how many years you have left to live. Am I recording? Yes, I am recording. What? Is that understood? Oh, do you want a different example? Okay, we'll do a different example. We'll have data with a lot of kids. We'll say, oh, I'll do sports. I like sports. We'll have data of a lot of games. We'll do if you win the game or lose the game, and how many goals are you going to score. So there are two different things that we want to predict.
Nothing for you?
Sports is not tragic, yeah. The idea here is this. If the two outcomes are related, if the two outcomes are not related, then that's what you should do. You should do two separate neural networks, one for this, one for this, of course. If the labels are related, for example, how many goals you're going to score is related to how likely it is you're going to win, right? In our example. So what we want to do is we think it will be beneficial to represent the data, let's say in a similar manner, or capture relevant information for both of the outputs at the same time. Okay, so we want to have one neural network that kind of represents the data. And then somewhere along the neural network, it can be early or it can be late. We'll have a split, okay? And then from the split, we will have two separate neural networks, one for each outcome. Is that clear?
You can just use let's call it the predicted goals you're gonna put as a feature in
but then you're going to predict goals, and then you're going to put a new neural network with all the information and goals, and then to predict if win or not. So the new neural network has to relearn all the representation of all the other features besides the goals, because you input like the player's strength and the weather and everything. So we want to avoid doing that. We want to learn some kind of a shared representation of all the other information that we have for the match.
So you don't consider the predicted goals as one of the features of the winning chance?
No, we don't want to do that, because had we considered the predicted goals as a feature for the winning percent, then we would use only one neural network to predict how likely it is you are going to win based on the goals. Mm-hmm. But what I want to do is, before the game starts, I want to predict both how many goals you're going to score and if you're going to win or not. I don't have that information. I want to predict both of them. Okay, that's a very good distinction to understand when you have to predict two data points. Okay, so this image is a split neural network. They decide to split it in the middle. Oh. No, this is not multi-label. Multi-label is one label per data point, but we will see. They split it after one layer. By the way, this, for some reason, the picture going from top to bottom, but we can imagine it going sideways. Do we want to rotate it? No, we'll be okay. Okay, so they put all the features, and then they have a new layer, and then they split it to small networks, okay? One to predict how many goals you're going to score, and the other to predict if you're going to win or lose, okay? At the end here, there should be one Y each. Now, when you update the parameters, when you back propagate, so these parameters are only based on how well they predict our goal number. These parameters will only be updated on how well they predict if we win or lose. But these parameters will be updated based on both how well they help us predict goal number and if we're going to win or lose. So so that way, both of the labels help us learn how to extract information, the useful information together. Is that understood? So by updating the parameters based on both outcomes, we're essentially training the network to extract information which is relevant for both outcomes. and only then later splitting it. And okay, so there's a difference between like the parameters which are shared and the later parameters which are split. Is that clear? I feel like the idea should be very clear. It's not very complicated. It's just something to know. People use it a lot. And then the consideration is, of course, when to split. Do I split early or do I split late? I've seen a network where they split only in the last layer, so that all the representation is together, and then only in the last layer they split, and it worked for them pretty well. But maybe had they split earlier, it would have worked better. So I don't know how to answer that. Is the idea clear? Yeah. Okay. Yes.
This is only something you do to preserve time, because otherwise, why is it not?
It's time, and there is a benefit here that you learn the shared information for goals and the probability of winning, which we believe are related. So when we learn the shared information, we ensure that the network kind of extracts the relevant information. In fact, by training it to predict how many goals you're going to score, it might even help it predict if it's going to win or not, because there's information in the goals which will back propagate, update the weights, and then we can use them. So they kind of help each other, not explicitly, only through the joint training, but they kind of help each other. And of course, to save time, that's clearly. The worry is that if you train a network separately, they will learn different representation entirely and kind of not converge well on the joint information there. That's what it is. Okay. Shir, you asked about multi-label output. So what did you mean by that? Okay, exactly. So this is still a simple multi-label output is when you have a classification problem with many classes, for example, objects that can be in a picture, and you want to say how many of these objects are in a picture. So usually what is done is a simple neural network that the last layer corresponds to all the objects that you have. So let's say you have 3 objects, dog, cat, bird. The last layer will be dog, cat, bird. And for each one separately, it will give the probability that it has a dog, probability that it has a cat, probability that it has a bird. But usually you don't split it to a new neural network. You just look at the last layer and compare it with the vector, which has 1 for every category that it has and 0 for every category that it doesn't have. So I would consider it more simple. And this is a more 2 different Y labels. So it could be what animal does it have? And then the second one would it be like, is it a picture that was I don't know, taken in a that won a competition or didn't win, or is it a nice picture or a disgusting picture? I don't know, something like that. Okay, awesome. Are we clear about this? Yeah. So this thing is a 1-to-many. Okay, so if we have 1-to-1, this is a 1-to-many. So I'm just okay, and I'm gonna all right. Now we're gonna move on to the really interesting stuff. What did you say? The colors? I took them from the internet. It's not me. We're going to move on to more complicated stuff. So the first new complicated data structure is an image-like. I'm calling it image-like. But I want to... Yes.
The first one is 1-to-1 if you have 3 outputs.
Okay, so first of all, I said, let's have it 1 output. I just took this picture, but I meant 1 output. And the reason is the X can have as many features as we want, right? When we say 1, it's 1 data point, and the Y is 1 label. So let's say it's a multi-class classification. So bird, dog, or cat, what's in here? It's 1 label, what's in here. So I still consider it 1-to-1. Okay. It's important because when we say 1, we mean 1 data point, which can have thousands of features. We don't know. And 1 Y is 1 label. which can also be a vector if it's a one hot encoded, or right, it doesn't have to be a number. Okay, image-like data, I'm calling it image-like, but we're going to explain. In tabular data, if I change the columns, the order of the columns around, does it matter? Let's say I have height and no, we are going sports. I have the temperature and the record so far, whatever. It doesn't matter which one's first and which one's last, right? In image-like data, there is an ordering. So the first point is that there is a, we'll call it a natural ordering. What do we want to call it? Logical ordering. An ordering of the features. In images, pixel 1 is next to pixel 2, and pixel 10 is next to pixel 11, but pixel 10 is not next to pixel. That's clear, right? Natural ordering. And then the second point of image-like data is that the information that we want can be located in different parts of or in different ones of the columns. So what do I mean by this? Let's say we want to classify if there's a cat in the picture. We can look for catness or cat-like representation in pixels 1 and 2, and we can look in pixels 9 and 10. We don't know where in the picture or where in the data point there will be the representation, okay? So the way I thought about saying this is that the features can appear, I don't want to say in the features. So I want to say the information can appear in different features or something that, like the catnet, the information for cat can be in the first pixels or the second pixel or the third pixel or the first 5 pixels or the last 5 pixels, okay? So what do we have to do with this image-like data? What do we have to do for it? Search it, exactly. You're making the right movement with your finger. What we have to do is search it. Some would say scan it, okay? And that's why a convolutional neural network was invented. So I'm going to explain. So what we need to do is to, I'm writing scan the picture. Okay, so there is, I'm going to start with this. Up till now, every time we move between layers in the fully connected network, it's a matrix multiplication, right? It's the values here times the matrix in the weights to get the new values, right? It's matrix multiplication, nonlinearity, matrix multiplication, nonlinearity, right? And we know from linear algebra that a matrix multiplication is a way to transform from one vector to another vector, right? We know. Here, we want to do a scanning mechanism. Do we know anything? So matrix multiplication obviously doesn't scan. It's not a scanning procedure. It moves from vector to vector. What do we know that scans or that does this thing where we look in the beginning and we look in the middle and we look at the end or something like that? Do we know what mathematical operation does this? Yes, but the other word of it is? A filter does it, yeah, but there's a broader word for it. It's the first word of CNNs. Convolution. So how does it? That's why we use convolution. So what is convolution? I really hope that's not how you spell it. So what is convolution? I have an image. Hopefully I have it here. Convolution is when you have, here is an example of a convolution of a vector with a window. The idea of convolution, the idea here is that we have a vector of size 6 and we have a window of size 3. So first we do these, the 3 weights times the first 3 values, and we add the sum of all the multiplication, right? So it's just the regular dot product, and then we get a value. Then we take the same window, we slide it one down, and we do the same thing, and we get another number. Okay? So
You start with A or you start with a little bit higher, like in C?
you start with C. So in C is when we slide it the other way, we have to fill with 0, so it's called 0 padding. Okay? But the idea is that a convolution, you take a sequence, and then you take a window, and then you do a multiplication in the beginning, get a number. So it's the sum of all the multiplication. You slide it one over, again, multiply, get a number, slide it one over, multiply, get a number, slide one over. Okay? And that's exactly the scanning procedure that we want to do in the images. That's why we use a convolution. The only problem is we don't know what window to use, what will be the weights. But we know that we want
You're talking about the number of the window or
the values.
values in the window itself?
The values in the window itself. We're gonna, that's what the model is gonna have to learn, what values to have it. You're going to define how many windows you want scanning. You can have 2 small windows of size 3 and 2 big windows of size 10 or whatever. You can decide what you want. And then the model will use gradient descent to find the best windows. And the hope is that these windows will scan for features which are relevant.
But if you're searching with 2 different windows,
Yeah.
you get like how do you
2 new vectors. One is the representation of the scans with the first window, and one is the representation of the scan with the second window. And then from these 2 new vectors, you can do a fully connected network to your outcome.
okay?
Okay? Or you can go on these 2 new vectors and do again a scanning procedure on the 2 new vectors, and again a scanning procedure, and then do a fully connected to your outcome. So you can have repeated convolutional layers, which do this scanning procedure. And then at the end of the convolutional layers, you go to your outcome. I'll show it. I'll show it. Okay, I'll do it here. Yeah, I'll do it here. This is another way to show it. This is a 2D convolution. 2D convolution is well defined. It's like convolution of the vector where you slide, but you slide with a matrix, and then you slide by row, and then you go down one column and you keep sliding. Okay, so this is the image. So we find these weights, and they're actually going to be 3 different sliding windows. The blue sliding window, which has certain weights, and then the green sliding window, and then the yellow sliding window. And at the end, we get the blue vector, which is or actually it's going to be a blue matrix, the green matrix, and the yellow matrix. Is that clear, the convolutional part?
No, I didn't get
Yes.
what. So you have 3 vector of the weights, and what you do. I mean, this is how the network learns with those 3. I mean, what are those vectors represent?
So the blue vector here, for example,
Because you mentioned
yes,
earlier
it would
that-
represent the value that you get from the blue window convolved with this area. And then here, the blue window convolved with this area.
Okay,
And then here, the blue window convolved. So let's say the blue window will be search for eyes, for example. So it will go step by step in our image. And every time there will be something that looks like eyes, it will get a high value. And every time there's something that doesn't look like eye, it will get a low value.
Okay.
And then we will get at the end a blue vector, which will say where there were things which look like eyes and where there were things which did not look like eyes. And
okay, so you said earlier that after that we want to do a convolution or something like that, and apply it in multiple in MLP in multiple layer.
yeah. So wait. So let's not confuse. You understood the idea of, let's say, searching for eyes. We're going to have an eye window that scans looking for eyes, looking for eyes, looking for eyes, and then at the end we're going to get
for the other eye in the picture.
For an eye in the
Okay.
picture, yeah. Or searches for X's, I don't know, searches for edges, or searches for whatever. What? No, but let's say it searches for eyes. Yes, in reality, it learns what to search for by itself. We can't predefine it. So it slides along and says at each point, what is the value here of the I window multiplied by the image? And if it fits, well, it's a high value. And if it doesn't fit at all, you get a low value. And it keeps sliding. And then we have a new window, a separate window, searches for, I don't know, squares. And then it slides and it gives me
But
what's a
it
square at
slides-
each point.
It doesn't slide on the picture, it slides on the.
No, they all
on the
slide on the
outputs.
picture. No, they all slide on the picture. We're going to have, let's say, 10 different sliding windows that slide on the picture. And then we're going to get 10
because
new
the-
vectors.
The inputs are the picture, okay.
Yes, it slides on the input
Yeah, yeah,
again
yeah,
and
yeah.
again and again.
Yeah,
And then we have an output. Now on this output, we can either use this as the new features and train a fully connected neural network to classify the image,
but
or
Right.
we can use one, we can slide again on this new features and slide over
I
them.
mean, by features, you mean to the next layer?
Yes.
Okay.
Yes. So what happens, what we usually do with a CNN is we use many windows to slide over the input and get many outputs. Then we downsample by using pooling to go from high dimensions, a lot of features that we get, to lower dimension. Then we slide again over the lower
Over the
dimension
the next
with
layer.
new windows. Yes, over the next layer with new windows. So the idea is that the first windows can detect simple things, let's say, can detect where there's an edge. And then the next layer, you can go over where there were edges and detect, let's say, where there were circles or something more complex. And then the next layer can detect where there were cats
And
already.
the dimensions of the next layer depends on the number of the windows, because every window.
Yes, exactly. So here is exactly a representation of what we said. Hopefully. Okay, so the answer was, how do you define how many windows you get? So here they go with 5 different windows. Each one slides over the input and gives a matrix. And then they do a downsampling, so the windows get smaller.
Do we know what downsample?
Yes, I didn't teach it yet, but we will learn how to downsample. And then they just take all these new things, linearize it, make it one big vector, and do a fully connected layer and discover what it was. Is that clear? Channels, what channels? So it's exactly like the idea of how many layers do we want. There is no one answer.
לא, איך אני מחליטה. פיזית בכל, איך
Yeah.
אומרים, יש לך בכל נגיד, פס הקרנל נגיד שווה 3.
Okay,
הגודל של הקרנל הוא 3 על 3.
yes.
אני מגדירה כמה קרנלים יהיו.
How do you do it in the code? I'll need to see it. I don't remember exactly. But
לא,
the question you asked is exactly the right thing. When you define a convolutional window, you define it to be the size, but you need to define how many windows of those you want to go on your input. So here there were 5. Okay, if you only do one, it's probably not going to be very helpful. The smart thing is to do many windows. One window will search for I don't know, circles. The other window will search for triangles, right? Something like that. Okay, I want to see. Okay, so that's one parameter. I want to talk about pooling. When we pool the data, pooling is the same thing as downsampling. There are 2 options. So this is pooling. One is max pooling and one is mean pooling. Max pooling says that for every, let's say 2 by 2 of input, we take the maximum, right? So here we take 6, here we take 8, here we take 4, here we take 8, and then we get a lower one. And the mean pooling is for every 2 by 2, we take the average, okay? It turns out that max pooling is very efficient because then it kind of extracts the maximum number here and discards all the numbers which are kind of close to 0. So they don't affect the average. So here, for example, here they did max pooling. So as far as I know, usually people do max pooling. You can also do mean pooling. Okay? Is this clear?
Yeah, it's reasonable you want the max pooling because you want it to be as fitted to the data as possible.
Exactly, and we suspect that high numbers here mean that there's a good relation, like the window, the convolutional window captured something here. So that's what we want to extract. And when there's a low number, we say, okay, there's nothing here, let's throw it away. Okay, it's clear. I want to say, so the things we can decide is we can decide how many windows to use, what will be the size of each window. Right here, it's size 3. How to do max pooling, right? And also how many times to do it, because we can take these max pooled and rerun another new convolutional layer on them, right?
How can you know you're not overfitting? I mean, you're using too many windows.
That's a good question. I don't have an answer to that. You might be overfitting. The best neural networks today for image recognition, they use, I have a picture of this.
Isn't she in Scotland, real?
Not that I know. Oh, where's the picture? The best one uses, I think, 6, let's do VGG network. 6, I think.
Because it depends on the number of the output of the input.
It depends on the number of the input, yeah. Okay, so they use, so the input is 224 pixels by 224 pixels by 3 colors. Okay, so they do it separately. And then they go, there are 64 windows here, and then they downsample to 28, and then they downsample to 56, downsample that to 128.
But it was
Wait. No, they downsample from 224 to 112, and then they downsample to 56.
They used 224 windows.
No, they used 64 windows of 224 of size. No, this is the output after you use the window. We need to read about this more. But the output after you use the window is 224 by 224 because it tells you at each position where there is. But 64 different windows they have. Okay, and then they have here 128 windows and 256 windows and more windows. And then at the end, there's a max pooling and then 3 fully connected layers and a softmax.
But if you're using more windows than the actual output, so the window will just you will be overfit.
So I agree with what you're saying. I think it's good practice to give it many windows so each window can try and learn, scan for something different, because each window we can think of it as a scanner for something, right? So if we have just 5 windows, it can only scan for 5 things. But if we have 200 windows, they can scan for 200 different things. Of course, there's a lot more parameters to learn, and you're a lot more prone to overfitting and everything. Yeah. So I understand that. I agree with that. To be honest, I don't really know what, I never trained an image like CNN, so I don't know best practices. Read what other people have done. I do know that they go for big sizes. They like big sizes, especially for real images.
The size of the window or the number of
number of windows. Okay. Yes, especially for images that are naturalistic images, so they can be variable. You know, you can have different colors and different things. If you do images which are all, let's say, MRIs, maybe you don't need as many windows because the images are more similar, but I don't know. Okay, so the last thing that you can also play with is the window size and the window stride and the window dilation. Sounds complicated. I'm just telling you here what they are. The window size obviously can be size 3 or size 5. Easy. The window stride means how many jumps, what do we jump? Do we jump 1 each, or do we jumps of 2 sizes, of 2 pixels or 3 pixels or so on? Okay, so here, for example, it's a jump of size 2, a stride of size 2. Okay, and the window dilation is, do we take all the pixels that are near each other, or do we sample them with spaces in between? Sometimes we want to sample them with a dilation in order to capture information that is a little bit across pixels and not just the pixels relate to each other. So for example, you can say, I want to have a neural network with 10 small windows of size 3 and 10 big windows of size 10 or size 30 and 10 windows with big strides to capture longer range data, okay, or something like that, or big dilations. Is that clear that how many things we can play with?
Yeah, you can play with, you can either do for the same layer window in the size of 3
Yeah.
weights, and on the same layer at the same time do another window with 10 weights.
Yes, that's what you want to do. Yeah, you want to do, because it can capture, it can scan for different things. Yeah, exactly. Very good. Okay, I think we're done with CNNs. At least we're done with what I wanted to say about them. And we're going to move on to the next data type. Oh, no, we're not done. I said CNNs are used for image-like data, but I want to show you that doesn't have to be for images. So I had an example. The example I had was EEG data for sleep, for example. So we know that EEG data, you have, let's say, an EEG electrode that recorded you while you were asleep. Let's say the task is to classify if you were asleep or not asleep. So you have a lot of EEG recordings, some when you were asleep, some when you weren't asleep, okay? There is an ordering of the features, right? The feature is just the value, the potential, the microvolt value at each time point. So there is an order, right? What's recorded at 10 o'clock is closer to what's the sample right after, and so on. But the information of when are we asleep, so there's something called sleep spindles, which are these, I want to show a picture, which are these yeah, they are these complicated, you see, activity that happens for a short time, and they can appear kind of any, why you do this to me? And they can appear kind of anywhere during the recording. Okay, so we don't know where in the recording it's going to appear. So what do we do? What's a good move to do? Do a convolutional neural network, right? On the, I just want to do the sleep spindles. On the EEG, that will kind of scan the EEG data, right? And have a window that will look for these spindles. Now, these spindles don't always look the same way, so you can't do it with one window. You'll want to have a lot of windows that can do for different spindles. And it can kind of scan, look for these spindles, and when it finds them, it can use it as a feature to say if you were asleep or not asleep. Is that clear? How it's not an image data, but because it has these two properties of ordering and the information can appear in different places, it's CNN is a good solution? Yeah, excellent. Obviously, you can go multidimensional, right? So an image, it can have the pixels in 3 different colors, right? And in EEG, you can have the EEG recordings with 64 different electrodes, but it doesn't matter, right? It's just, it's adding another dimension to the data, but you still scan it. You'll just scan all the 64 electrodes, okay? Okay, I'm done with CNNs. I'm just gonna write this big. Convolution. I don't know how to spell it. I'm writing CNNs. Okay. The next type of complicated data structure is sequential data. What is sequential data? Yeah, so it has, so time, you said Zman is time, yes. So the idea is that the data points, not the features inside the data point, the data points themselves have an ordering. Usually it's a time ordering. So you sample the data points at day 1, at day 2, at day 3, at day 4. A sequential order. It's almost always in time. We'll give, okay, so it's in time. And then the second thing is that, and this is very important, history matters. So No, I have to give an example of the patient that comes every year to the doctor, and you measure all the information about the patient, his age, weight, blood, or whatever, and you want to classify if he's sick or not. So we can't just use every visit as a separate visit and do a regular neural network, right? But here there's something about the history of the patient that matters, because what was his weight last year versus what his weight this year kind of matters. So we want to be able to handle the sequence. Okay, I think also in soccer, history matters. You have the matches, but the winning depends on how you played last game. I think it affects how the players play. Okay, I said it's almost always in time, right? The EG is another example of something in time. Every time point we sample all the 64 electrodes, but it doesn't have to be in time. What is an example of a sequence that is not in time, that has these properties? A written sentence. You have a written sentence, each word can be thought of a data point, and they come in a sequence, but the history matters. The word, I don't know, well, no, it's written sentence. There is no time here. Yeah, it's just the text. So the word, I don't know, funny is different if you say, the person I met was very funny versus the food I tasted was funny, right? It's a different meaning of the word funny. So the history matters. Okay, so what do we do with sequential data?
RNN.
Excellent. What is an RNN? By the way, there are 3 solutions to sequential data. So the first one is RNN, which is a recurrent neural network. Yeah, thank God. Which I'm telling you right now, when they came out, when recurrent neural networks came, they changed, everybody loved them. And to this day, everybody really, really likes recurrent neural networks. Oh, I forgot to say that when you have sequential data, you have 2 more types of problems. One is a many-to-one. Okay, so here at the bottom, we have the X data point coming in at time 1, at time 2, and at time 3. A many-to-one, it says, give me the whole sequence, and then I'll give you one label per sequence. So give me the whole sentence, and I'll tell you if the sentence was, I don't know, happy or sad or something like that. Many-to-many is you give the data points in order, and in each time you have a label. So every time you visit the doctor, you say if he's sick or not. Or every time you go to play the match, you say if you win or not. But the label at time 3 depends on the data on time 3, but also on the data on time 2 and the data on time 1, because history matters. Okay, is that clear? Excellent. Thankfully, all of the models we're going to learn can do both tasks. It's very simple. It's just if you decide to add an output layer or not. Recurrent neural network. The idea is very simple. Here is the idea. Up to now, a simple neural network was Y predicted. It was a function of some input, right? F of X, right? Excellent. We're changing it to be Y predicted is the function of an X and some history, okay? But here's the trick. This is Y predicted at time 1, okay?
Why not call it X? I mean, the history is the X before.
Almost, because I'll show you right now. Y predicted at time 2 will also be F of, oh, I'm sorry. Of course, this is X at time 1, and this, your idea is close, but it's almost, is X2 and history. But history at time 2 will actually be what? Yes, it will be based on Y1, but it will actually be a hidden state in the Y1 architecture. Okay? So when I said H was for history, I actually meant it's for a hidden state. Okay? And a hidden state is literally the hidden layer. Okay? So I'm going to say Y1, there is no hidden layer, so it's just a function of X1. But actually you can think of it as a function. How do I want to write it? We go x1 to a hidden state, right? With matrix multiplication, hidden state 1 to y1. Right? Is that clear? This is a one layer, right? We go into a hidden layer. We know this, right? Meet, you're with us? Okay. But y2, here's what we do. We go from x1 and, I'm sorry, x2. We go from the second input and the hidden state of the previous term to a new hidden state to a new y2. Okay? So that way we can use the history. And then, well, it depends. The y depends if we're on many to many and then we do need them, or on many to one, where we just cut the y out and we just go hidden states, hidden states, hidden states. Okay? Y3 will be a function of x3 and a hidden state, but it will actually be a function of x3 plus the hidden state 2, right? Which will map to a hidden state 3, which will map to a y3.
In state one.
What? No, of 2, because it's 3. Okay, is this clear? Now I want to show you how this illustration illustrates it in two different ways. One of the ways we're going to focus on here, we say we put x at t-1 and we do a neural network, and we can go for y, we don't have to, but we get an a at t-1 and we get these w's. This is the state, and then at y time t we get both the x at time t and the history from the previous time. We do a neural network and we go to yt, we don't have to, and we go on again and again and again. Or you can just do it with this recurrent arrow example, that at every time you go xt, put in the neural network, yt, and then you go xt and the hidden state of the previous time you used it, and you go. What's the most clever about this is that it works for different length of sequences. It can work if you have a length of 5 games and just put it 5 times, or 700 games, you just put it 700 games. Right? It can keep working. You don't have to define beforehand what is the length of your sequence, what is your input. You only have to define how many features you measured at each time, which is what we usually do. Okay? Is the RNN clear?
Yeah.
Yeah? Okay. What are the two big problems of RNNs? Let's see if I remember.
Go on.
Yes. So what is it?
For memory. Base em cima da.
Excellent. No, they have one problem. I'm sorry, I misremembered. That was the problem that you said. RNNs have a memory problem. What does this mean? When we want to model long-term dependencies, let's say the meaning of the word right now depends on what the meaning was 70 words ago. It can happen. There are stories like that. By the time we reach this word, the hidden states we go through 70 new hidden states every time. So it's very likely that word will not have an effect anymore on this word. Okay, they have a memory problem. Every time you rewrite the hidden state, so you lose information, maybe a little bit, but when you do it over many, many times, you lose that information. Okay. A different way to see this problem is, we talked about the vanishing gradients problem. Remember that if we have many, many, many layers, things that happen in the early layer don't affect the output. So here, something that happens at x70 ago will not affect the output here at x1. So it's like the vanishing gradient. Okay, so if you're familiar with that, it's the same thing of saying the same thing. Okay, so how do we solve this memory problem? Very good. We use an LSTM network, which is long short-term memory.
Long short?
Yeah, so you have a long short-term memory. So you have you can hold in your head a short-term memory for a long time, okay? So it's a long, short-term memory. And here is, what is the big difference between LSTMs and RNNs? What is the big difference? The big difference is that you separate the hidden state. You have a separate hidden state, and you don't have to update every time. You keep the hidden state separately, okay? And then every time you get a new input, you run the neural network calculations on it to see if it goes to Y or not. And separately, you decide how do we want to update this memory state, this hidden cell state, okay? So the right name for it, I would say, is instead of the layer, the hidden layer being a hidden state, we keep a separate, and the separate is what's important, cell state, where at each time point we can decide to update it or change it or not.
How do you know if you want to change it or not?
Excellent. So that's what the neural network has to learn. It has to learn this parameter as well. So it has to learn how to represent the information, and it has to learn, do we update the cell state or not? So it learns it based on if the new data, if the data point that I got right now is very interesting, is very important, it adds a lot of new information, let's update the cell state. And if the data point that I'm getting right now is not very interesting, is boring, let's not update the cell state. We can keep doing it. The example I have is with words. There are probably examples in time. Let's do it in time. In time, visits to doctor. Let's say you go year after year, and the new year, it's not very different from the previous year. So you don't want to update the cell state.
But I would say on the contrary, because if you don't need to update, what do you care? What do you care in updating? Because there's not a lot of change. So there's not a lot. I mean, if I went to the doctor for
Yeah.
like 60 times,
Yeah.
and on the 60th time, something happened,
Yeah.
and I want the first time to affect the 60th time.
Yeah.
This is our problem.
Yeah.
But if for the 59 time, the first times, I didn't change a lot, so it will kind of be like I was looking at the first.
Exactly. That's how it will be. This is what it comes to solve. That when you don't change a lot for the 59 times, the information in the first
But
time
yeah,
is
I mean,
still
that is
represented.
as well, because
No, because
you don't change. I don't change a lot during the 59 first time.
yes, but in the RNN, every time you change your hidden state, because every
But
time
I
there's
don't
something,
change it a lot because
you don't change a lot, but there will be something different. So we think of 59 new changes as being cumulatively different.
okay,
It's a lot of small changes add up to a big change.
okay,
RNNs are very good for 5, 6 steps backwards. I mean, 10, 12.
okay,
When you get to 20, 30, 40, they just can't do it.
okay.
Okay, so that's LSTM. And I just want to show a picture, but you really don't have to learn this picture or focus on it. The picture is that, again, it's like the RNN, except inside here, you go separately to a cell state and you decide if to update or not, and to your hidden state or to your outcome if you want. Okay, so that's
like define a threshold for the difference between the two layers, and this is how you decide.
so
whether you want-
yes, you can do it on the difference, or you can just do it on the information in this layer. Let's see what this layer is, on the information in this data point. Let's see what this data point is giving me, and do I decide it's interesting information, I'll update, or I can discard that information and keep predicting well,
Okay.
and my loss won't be affected.
Okay.
Okay, awesome. I want to do transformer architecture briefly, but I just want to make sure it's clear how they can both be adapted for both many-to-one and many-to-many. The question is, at each time point, do we add an output layer or not? We can just have done the same RNN without an output layer, and at the end, go to an output layer. So it solves many-to-one and many-to-many, okay? Excellent. Now we get a new architecture. It's a transformer architecture, which I'm not going to be talking a lot about, but I will say the transformer architecture was invented in 2017, so it's very new. And that is what kind of transformed the world, if you want to say, because it is much, much better than all the LSTMs and the RNNs. What is the big idea of the transformer architecture? The transformer architecture says, instead of inputting each data point sequentially, right? Putting the data point, doing something hidden state or whatever, and then putting the next one, and then just treating the hidden state. We treat all the data points as input, and for every data point that we have, we decide to look backwards over all of the data points that we got until now and see which ones of these do I use now and which ones of these do I not use. Okay? A different way to say it is this. Instead of compressing all the information from all the previous data points into a hidden state or a cell state, and then just using that, we have every time we reach a new data point, we can look back on all the previous data points and decide which ones to compress and which ones not to compress. Is that clear? Now, this turns out to be very, very good. What? No? Yes. And this is, oh, good question. That is called an attention mechanism, which means at every data point, we got at data point 70, we look over the past data points and we decide which ones to pay attention to and which ones not to pay attention to. Now, this is very good because it can be dynamic. It can be that, for example, again, in a sentence, you encounter a word which has to pay a lot of attention to a word 10 words back. And then the next word has to pay a lot of attention to a word 2 words back. And then the next word has to pay a lot of attention to a word 7 words back or something like that. So for each data point, you learn for each one of the previous data points, which ones to pay attention to. And this is the attention mechanism. Is that clear? Now you might say, okay, that requires learning a lot more parameters because instead of learning just the regular parameters, you also have to learn the attention parameters, which they are stored in what's called an attention head. Attention head is like the layer that is like the vector that decides which one of the previous inputs do we pay attention to. And that's true. And that's why transformer architectures require a lot of computation to train because there's a lot more parameters. You have to keep your regular matrix multiplication parameters and nonlinearities and your attention parameters, which tell you which ones of the previous data points to pay attention to. Okay, excellent. I want to show an example. There are 2 examples which kind of bring the point home. This is the first example. So here we have, again, this is showing, I'm so sorry that some of the pictures go sideways and left to right and some go up to down. So this goes left to right and up down is at time point. So this is X at time point 1, X at time point 2, X at time point 3. We run one fully connected layer just to give it a representation that we can work with, okay? We don't have to. And then here, for this X at time point 1, we decide which ones, or I should say X at time point 4 or whatever, we decide which ones to pay attention to, how much. So here we pay 0.6 attention to X3, 0.3 attention to X2, and 0.1 attention to X1. So most of the attention is used from X3. And then we have the next one, and that pays 0.5 attention to X1, 0.2 to X2, and 0.3 to X3. So it actually pays more attention to X1. And then we have the next one, which pays 0.7 to X3, 0.2 to X2, and 0.1 to X1. So it pays, okay, so you see how the attention can change for every new data point. Is this clear?
No,
Okay, why not?
because I thought you're just looking back, but in C,
Yeah.
you also look forward.
Okay, you're right. This is an encoding mechanism. Yeah, this is the self-attention. In the self-attention is a way to encode the data, is you go backwards and forwards. Okay. And what I talked about the transformer is only the decoder mechanism, which only looks backwards. So yeah, the picture is confusing, but let's treat this as 0.4, 0.5, and 0.6, okay? and let's say 0.6 doesn't decode from 0.5 and 0.4. Okay. Excellent. It turns out that this architecture can solve a new problem, which is called sequence to sequence. Now, sequence to sequence can be solved with RNNs and LSTMs, but they are really the best way to do it is with transformers. Sequence to sequence is you give a sequence, it can be of length 3, and then you have a new different sequence of it could be a different length of outputs. So the best example that people give is machine translation. You give a sentence in English, which can be 3 words, and translate it to French, which it can be 3 words, but it can be 7 words, right? And how do you do it? So the way the transformer architecture works to do it is that it takes in all the sequence of X, and then it starts translating. In the beginning, it will pay attention in French to the words in English which matter most for the beginning. And then as we unfold the sentence in French, the attention will also shift. What do I mean by that? Yes, but this is the example that people give. So let's say this was from French to English, I think. So when you have the first word, comme, you see this line is the boldest because it pays most attention to like, because that's what it's trying to translate now. And then dance is in, and set is example. But example, it actually pays more attention to this input, because in French you say exemple simple, I think, instead of simple example. You switch them around. And then in simple, it will pay attention to this part. Okay, so that's why attention helps us also with the sequence to sequence problems, because you build a sequence that can pay attention to different parts in the early sequence. So it can also help us with our sequential data and also with the sequence to sequence. Okay.
Wait, but
Yes.
But the attention should go to the early word in the French sentence, not in the English sentence.
So it depends if you put in what is X and what is Y here.
So let's say you want to translate the
I'm
English to French.
Yeah, X.
So the attention should go. I mean, you don't know the Y yet, so the attention should go from in to like, and this to like, and simple to like.
So you're in your first Y, you don't know what to predict yet. So you have put in all your X's. Since you're in your first Y, you're going to go most of the attention to the first word and a little bit of attention to in, and then a little bit of attention to the end. I don't know, that's how the model works. You put the first word, and now you put in, you're on your second word. So you already know that you have the comme. So you know you're ignoring, yes, you know you're ignoring like, so you're putting most of the attention on in. That's the next thing I'm trying to transfer. I have some attention on this. And I also have some attention on like to make sure I translated it.
You don't want to give attention to the word like either.
So it gives some attention here, you see, but it gives less attention because it knows in comme I already translated it, because the internal representation of the input sequence and comme says I'm on my second word. I'm already probably paid attention. You know, I already use it. Yeah, it's a little unclear. Okay, and there's a lot of hand waving going on here because I don't know the full math behind it. But I want to. The important thing that I want to drive home, and this is important, is transformers use attention mechanism, which allows a much better way to look at your history, because instead of compressing all the history to a hidden state or a cell state, you can decide at every point in time which parts of history do I want to look at right now. Okay, and I'll say, and this changed the world. No, I don't want to say this changed the world, but and this is very, very big. Okay, excellent. We're not done. Are we done with the sequential data understanding? Because I want to show a trick with sequential data, and then we'll be done. It turns out that sequential data have another task. It's not many to one, it's not many to many, it's not sequence to sequence. Sequential data have a task which is called sequence modeling, which I like to call many to next. What do I mean by this? You put in X at time point 1, and you want to predict what will be X at time point 2. And then you put X at time points 1 and 2, and you want to predict what will be X at time point 3. Put in X at 1, 2, 3, you want to predict what will be at time point 4. Okay, so that's what I mean. Okay, so this is called sequence modeling. So for example, if you do it for language, you give in the words and you say what the next word will be, it's called language modeling. If you do it for, I don't know, EG data, you give it EG and you want to predict what will be the next value, it can be EG modeling.
The math, I don't know, I forgot his name. This sequence, not Bernoulli.
Fibonacci.
Fibonacci.
Yeah, Fibonacci, it's easy to do Fibonacci
Yeah.
modeling. You only look at the last two. But in language modeling was considered to be one of the hardest tasks in all of computer science. How to predict the next word given a string of words, right? It's very difficult. Now, two things I want to say. First of all, sequence modeling is why do people like it? Let's go. Why do researchers like sequence modeling? It auto completes me. Yes, right. Your autocomplete on your phone is also no, but I meant to say what's easy about sequence modeling tasks. I should say about sequence modeling data. That there is a lot. Yeah, but why is it? I'm not asking the right question. The question is, okay, I'll just say the answer. The answer is for sequence modeling, you don't need labels. You don't need label data. You just need to record the sequence, right? You just need to record the sequence. So for example, if we want to, I don't know, do machine translation, we need hundreds of thousands of sentences in English and in French and the connection between them, pairs of sentences. And some poor humans had to go write down all the sentences and say, this is a good translation, this is a bad translation, or something like that. And it takes years to build up these databases. But for self-supervised, we just take the text. We just take the sequence, right? No, you don't need no logic. What you need is to give it sequences. Then you take every sequence and you give it the first one, say what's next. Give it the first two, what's next. First three, what's next? And you already have the what's next in your sequence, right? Of course you train it, but you don't need to build a database that has X's and Y's. You just take your X. And it turns out has been revolutionary because to find large sequences, it's easy to find. It's easy to record data. The problem is to attach labels to the data, right? Awesome. And then the answer is written here, but I want to ask a question. When we do this kind of task, is it supervised or unsupervised learning?
It's self-supervised.
Yes. So what is self-supervised? It's its own thing, right? It's not supervised because we don't have labels, and it's not exactly unsupervised because we do have a loss function. We do have a predicted X, and we compare it to the X that needs to be, right? Self-supervised. Excellent. What did I want to say about self-supervised? Oh, I did want to say, we did meet one architecture that was self-supervised already, but we didn't call it that way. Who remembers? Autoencoder. Remember, the autoencoder was the way to go from X down to a bottleneck and to reconstructed X. And then we compared how well we did. Do you remember this? In the dimensionality reduction, we had, you know what? I'm thinking. I think if we have 15 minutes and if we have time, we can go through autoencoders now, again, full of them, and then we don't have to do it next week. What do you think? Yeah, okay, so we'll do that. Okay. Does everybody understand self-supervised? What self-supervised means? Does everyone understand why self-supervised is amazing? It saves us a lot of time. It's phenomenal. Excellent. Next week, we will learn even more reasons why it's good. Next week will be the last week. I do want to, now that we open self-supervised, we'll talk about more self-supervised examples. Before I leave sequential data, oh, and obviously you don't need a transformer for this, right? You can do an RNN or an LSTM or any other sequential data, right? Because you just predict the next data, okay? I do want to say, today we don't only use a simple RNN or an LSTM, but we use what's called a stacked RNN or LSTM. So what do I mean by that? Remember that in the RNN, we went to the first hidden layer, and then we used that hidden layer to go to Y and for the next one. But we know that we can have a neural network with 3 hidden layers, right? So what can we do for an RNN? Yeah, we have 3 inputs. So we can go from X2 and the hidden layer 1 of X1 and the hidden layer 2 of X1 and the hidden layer 3 of X1. All 4 of these things go together to Y. Okay, and so here is a picture of a stacked LSTM. So we go from X1 and we have our first LSTM, which has a cell state, right? And then it can keep going to a second LSTM, which has a different cell state, and to a third LSTM, which has a different cell state. And then you go to X2. And then in the first layer, it takes in X2 and the cell state from the first LSTM. You can go to the second layer. The second layer takes in the representation from here, matrix multiplication, nonlinearity. We know this, like go to the next layer. And the cell state from this layer, okay? So we stack them up, okay? So we can also stack up the attention heads of the transformer. We can say, in this layer, you pay attention to this and this and this words previously. And then in this layer, you pay attention to that and that and that words previously, right? Excellent. So this is the one thing I want to say, that we usually stack them up and we can have many attention layers, which is similar to saying we just have many hidden layers or many hidden states, right? And so we can kind of, I hope I'm not losing you guys. I feel like it's not so difficult if you look at each time point as its own many layered neural network, but then we have in different time points and we just use the history from the previous neural networks. Okay, so that's how it works, okay? Last thing I want to say, a good benefit about self-supervised many-to-next is that it's very easy to turn it generative. What does it mean? What does it mean? Turn generative. In Hebrew, legenret. No, I was kidding. Because computer scientists in Hebrew say legenret. How do you turn it generative? I have a self-supervised model which I trained on a sequence. I modeled the sequence very well. I want to turn it generative. How do I do it? Oli, how do I turn it generative? My many-to-next self-supervised model. Let's say it's a language model. What? No, I trained it already. It's already well trained. It can already predict the next output based on my input. Now I want to turn it generative. I want it to tell me a story. What do I do?
You repeat a sentence.
You put a sentence and then you get one word. Okay.
So you repeat it for the next word.
Exactly. So the trick is you put in a sentence, you get in the predicted word, then you treat that predicted word as real, and then you put in the new sentence with the predicted word, and you get the next word, and you get the next word, and you get the next word. And this is why it's very easy to turn them generative. Okay? Excellent. Next week, so here's what I'm going to do. In the last 10 minutes, we're going to finish self-supervised. And then next week, we're going to talk a little bit about different tricks to turn other models generative. But every sequence model to turn it generative is very easy. You just take its input as real, right? As the predicted next, as the real next, and you just plug it in and you keep going. Okay, excellent. And now comes something that I wanted to reveal. We all know GPT.
What?
You don't know GPT, Sheila? So what does GPT do? It does exactly that. You give it a sentence and then it predicts next word, next word, next word, next word, next word. What? No, but that's what it does, right? It was trained on language modeling, which means I give you a lot of text from the internet, and you have to, we divide into sequences. I give you the sequence, you have to tell me what's next. You use attention layers to say which ones. GPT-3 has something 90, 100 hidden layers, but also has something like 16 attention layers, right? So it's stacked a lot of different attention layers or something like that. Okay, we don't know exactly. What does GPT stand for? This is the big thing.
Generative.
It's generative. What does it mean that's generative? That it has that trick that you turn it on and it keeps generating. Pre-trained. What does it mean pre-trained? No. Uman kvar. That's better. It was already trained. Someone else did all the training. What? No. Someone else already did the training. Who did the training in this case? A company, OpenAI. And what is the T? Okay. So GPT is a generative. We know what it means. Pre-trained means we don't have to update the weights. It already found the weights. Transformer means it uses the transformer architecture with the attention layers. Is that clear? Now we know what GPT is. We can go to the Shabbat table with our parents and say, I know what GPT stands for, and I can explain what it is.
They can do it too. They can just Google it.
But they don't know what a generative transformer is.
Okay.
Okay, and pre-trained just means someone else trained it. Okay. Since what are you saying now? Your parents want to teach GPT? Yeah, it's important. Okay. Okay. We finished with the complex data types. There are maybe more complex data types that we didn't cover, but I don't know how to teach them or how to cover them. Okay, but generally the important thing is that we have the simple data or simple data with a lot of output. Then we have image-like data, and which use CNNs, and sequential data, which use one of the sequential models. Okay, because we mentioned self-supervised learning, I want to pivot and talk for 10 minutes. That's it, on self-supervised learning, and finish that chapter. And then next week we will talk about generative models, which we also mentioned today, and we'll talk about interpretability, which I think is just interesting, and that's what a lot of modern things do. And we will talk about the modern, really modern machine learning tasks, like really what's tips and tricks you can use today, which will make your life much easier. Okay, so I think it's worth it to come next week. Okay, do I want to open a new board for? No, I'll just do it. So I'm doing here self-supervised. So besides the self-supervised of the sequence tasks, we learned, which we know what it is. It's just the sequence modeling, predict the next one. We learned about auto encoders. And I want to mention in 10 minutes, maybe I'll do it next week. Maybe we'll finish now and we'll do it next week. What do you think? I feel like it might take more than 10 minutes. Okay, we'll do 2 autoencoders now. We'll just remind what they were, and then we'll continue next week. So the first autoencoder was an autoencoder for dimensionality reduction. So I'm just reminding, we put an input, the input can be this 4. We have an encoder, which is a neural network with as many layers as we want, and they go down in dimension to a bottleneck. We said it's very important that in the middle, the representation here has less dimensions or less feature than here, because that's exactly what we're doing. We're reducing the dimensionality. And then a decoder reconstructs the data, and then we compare. Oh, wow, that's a very good reconstruction. This looks almost identical. Probably has very low loss. Right? What? Maybe they cheated, they lied. Okay, I don't know. And then when we do this, we can use the bottleneck as a compressed representation. Okay, remember this? Excellent. So this is a regular autoencoder for dimensionality reduction. There's also a sparse autoencoder for dimensionality reduction, which does the same thing, I promise you, except that in the middle layer, instead of being just a bottleneck, it also tries that only few of the neurons will fire. Only few of the neurons will give a value different than 0. Okay, why is it doing that? Because essentially, okay, so I'm going to say it again. Here we just wanted it to have a low representation. So let's say we started with 100 features, we go down to 10 features. So it will be a vector of size 10, but we don't mind if the vector of size 10, all the numbers are continuous. They can be positive numbers, negative numbers, anything. It's just a 10-dimensional representation of the data. Here we say, no, we go from 100 to 10, but also we're going to make all the 10s, as many of them as possible, be 0 and have few of them equal a number. This way, the layer, it can be thought of as a layer of features that are on or off. All the features that are 0 are like off, irrelevant for this data point, and all the features that are 1 or a big number are relevant. So this is a sparse autoencoder. Sparse just means we want to have as many of the features, the values 0 as possible, while still conserving the data. Okay, and then we say, oh, look, this data point activated the nodes 1, 10, and 12. That means something about it. And then the next data point activated 3, 7, and 8. That means something else about it, right? When we have the sparsity constraint, we can say that, and we don't have it with the bottleneck here, where every data point probably activates all 10 of the feature of the nodes. Okay, is that clear? Excellent. And now we're going to be talking about yeah, I think we're done. I think we covered it in dimensionality reduction. I think this was clear. Now we're going to be talking about autoencoders for denoising, which is the last thing I'll do. And then the next autoencoders, they're the generative autoencoders we're going to be talking about next week, when we're going to be talking about generative models. Autoencoders for denoising, it's also self-supervised. What do? You take your data that you collected, no labels, you don't have to label it, but you destroy it a little bit. You set some of them to 0, or you add some noise, or you add some random noise, okay? Bechavana, on purpose, you destroy it. Yes, wait, Shira, wait. And then you put the destroyed data point as your input, but we want the autoencoder to encode it into the bottleneck and to decode it and to reconstruct it to be not destroyed. The loss function is how well do you reconstruct it to the not destroyed data. Okay, So this is clear why it's self-supervised. There is no label. We just collect a lot of data points. Each data point is its own label, right? Because that's the autoencoder, it encodes itself. But we also kind of destroy it on the way. Why is this very good? Oh, that's what we're talking about next week, about how you can how you can turn it generative to generate new pictures without noise. But here you can put a next picture with noise and it will just clean out the noise. This is very useful in audio processing, right? You have a lot of crisp recordings, and then you add random noise to them, and you get the model to clean out the random noise and go back to the original one. You're thinking of images to sharpen or unblur. Yeah, so here in the example, this is exactly what they're doing, right? But I'm saying in audio processing is somewhere else, that it's very likely that by accident, one day you record, I don't know, your radio show or whatever, your podcast, and there was noise, right? But you have a lot of good samples of clean data. So you add noise to the clean data, train the autoencoder, and then that one day when you have noise, you just feed it to the autoencoder and cleans it automatically. I think it's a good example. Okay, so in general, I want to say two things. Self-supervised learning is my favorite learning because you don't have to build a database with inputs and outputs or labels, right? You just take the data and use the data itself, and you can do all kinds of crazy things like learn how to clean the data or learn how to reduce the dimensionality of the data. Or if you have a sequence data, you can do a GPT type thing. What? So are you talking about the denoising autoencoder or about how would you know? So you're asking, would it work on text? Yes, great example. That's what I wanted to say. You can put in text with typos and see if a denoising autoencoder will correct the typos back to the original text. So you have to have clean text, you feed it in with typos, and you see if it manages to clean it back to the clean text. Excellent. That's a good use case. Okay. So as I said, next week, so what did we learn today? Today we learned about complex data types, complex architectures, mostly CNNs and RNN LSTM transformer, which are all sequential, and we learned about self-supervised. Next week, we're going to learn about generative models, interpretability, and really modern machine learning, how to do the easiest, quickest tricks. Yeah, there will be a big secret revealed next week, which it's worth it to come. Okay? I'm done. Any question?
חיים, את לא מבינה כמה CNN זה חודש, אצל אייל חודש שלם? את אומרת CNN?
רגע, any questions or I'm closing the recording? No?
לא עדיף.
נכון, אבל עכשיו כן, יש לך רגע את הבסיס ואז נכנסים לתהום